Okay, so we've been talking about gases, and we just started talking about there at the end gas stoichiometry. So we did an example. So let's try another gas stoichiometry sample here. So take a couple minutes and see what you come up with. Again, follow the steps that we talked about. Really, again, it's the same sort of 4 steps that we use in a regular stoichiometry problem, with somewhere along the way there, the ideal gas law oftentimes again being used. So in this case, this is pretty much like the first experiment that we did. The magnesium with the hydrochloric acid, where you tied the magnesium to the string and you react it with hydrochloric acid. So we want to know, what is the volume hydrogen gas at STP from reacting 5 grams of magnesium with excess HCl, and magnesium there is 2431 there on the periodic table. All right, so take a couple minutes and see what you come up with. I'll do it as well. Hopefully you come up with it's involving gases. And again, like I said, this is pretty much identical to the one from the first gas experiment we did, calculation. So in this case, we eventually want to figure out the volume of H2 at STP. A reminder that STP is obviously 273 for the temperature, and our pressure is 1 atmosphere. So again, if we think about PV equals nRT for our hydrogen gas, we do have the pressure, we do have the temperature, we do have R, and we eventually want the volume. So once again here, we are going to use stoichiometry to figure out the moles of the hydrogen gas. So with that being said, we'll just roll into our normal stoichiometry here. We have a balanced equation. We're going to take what they gave us, which was 5 grams of magnesium. We're going to convert that into moles. So we'll divide by 2431. Once again, if we stopped at this point, we would be in moles of magnesium, which is close to what we want, but we do want actually to get over to hydrogen. So we will use the stoichiometry from the equation, which looks like it is a 1-to-1 relationship. 1 mole of magnesium from the equation gives us 1 mole of hydrogen. And if we do all that there, will give us 5 divided by basically 2431. Going to get us 0.206 moles of hydrogen. So this would be kind of like the third step in the stoichiometry scheme, using the balanced equation and the multiple relationship between basically these 2 guys here, which is a 1-to-1 relationship. At this point, this is really where we're going to now deviate into the gas law here, and we could use PV equals nRT. In this case, we're going to solve for volume, so we'll send pressure to the other side. Volume will equal nRT divided by V. Putting in our numbers here, 0.206 moles of hydrogen, 0.08206 are our gas constant, and our temperature of 273 Kelvin, all divided by our pressure of 1 atmosphere, which is our standard pressure. Kelvins cancel, moles cancel, and also atmospheres cancel. Gives us 0.206 times 0.08206. 0.206 times 0.08206 times a 273er. Gets us somewhere in the ballpark of 4.61 liters as well. First off, any question on that calculation? Could I have solved this problem differently? The answer is yes in this case. So because we were at STP, this could have been a situation where you could have used 1 mole of a gas is 22.414 liters. So you really could have done the first part here, and that would have gave you 0.206 moles of hydrogen. And at that point, you could have just went into this reaction here, or conversion. And with rounding, you should be pretty much the same answer there. In this case, I got 4.62 with the rounding, but pretty close to the same answer at that point. So this is a place where you could use that little conversion that we saw. Once again, we could use it because we are at STP, so that's in play. Once again, you cannot use it if it is not STP. But if you cannot remember, just like we did above, you could have used the ideal gas law. Yes. Yeah. So that's that relationship that we saw when we were talking about STP earlier. And when it is at STP conditions, 1 mole of any gas will equal 22.414 liters. So as you can see here, it can shortcut out the ideal gas law. But if you're not sure, you can always use the ideal gas law in any situation. Yeah. Other questions on that there? All right, so let's talk a little bit about one more stoichiometry type of situation, which is sort of that Avogadro's law that we were talking about earlier. And sort of how it sort of works here with stoichiometry. Remember, this is at constant temperature and pressure. So let's just say that we had an equation of 3H2 plus N2 gives us some NH3. And let's say that we are starting with 5 liters of H2. We want to know how many liters of NH3 at, we'll just make up 295 Kelvin and 1.35 atmospheres. So in this particular case here, you could really approach it 2 ways. And I think this was kind of an earlier question that was asked as well, is like, when might you need to use the ideal gas law twice? And this would be a situation where you could use the ideal gas law twice. So we eventually want to get over to NH3. And in this case, we have the temperature, we also have the pressure. And in this case, we actually have 2 volumes for 2 different gases that we're looking for. Right? So if we started with the H2, we could actually use PV equals nRT and actually solve for moles, because we know the pressure, we know the temperature, and we know R, and we know the volume for the hydrogen gas. So if we do that, N would equal PV over RT, and this would be everything for the hydrogen gas part. And if we put in our information here, our pressure would be 1.35 atmospheres. We have our volume of, not that, we have our volume of 5. So our volume here is 5 liters. And our R is 0.08206. And our temperature here is 295 Kelvin. So if we do all this for hydrogen here, we will end up with 1.35 times 5 divided by 0.08206 and divided by 295 gets us something like 0.279 moles of hydrogen. We once again could do stoichiometry at this point between hydrogen and NH3, and we see that we have 0.279 moles of H2, 3 moles of H2 from the equation gives us 2 moles of NH3, bless you. And that gives us 0.279 times 2 divided by 3 gives us 0.186 moles of NH3. Now, if we think about the NH3 at this point, we now have moles. We still have the same pressure and the same temperature as their constant. That means at this point, we could go into PV equals nRT and solve for volume for our NH3. And that would be nRT divided by P. And in our numbers here, I'll rewrite it over here, NH3. We have our moles that we just got from our stoichiometry. We have our R. And we have our T, which was 295 Kelvin, divided by our pressure of 1.35 atmospheres here. So putting that in, we get 0.186 times 0.08206 times 295 divided by 1.35 gets us a volume of, we'll call it 3.33 liters, give or take, or 4, we'll round to 4. So this would be a stoichiometry problem where we actually did use the ideal gas law in both situations, kind of before and after here. Again, balancing the equation, converting to moles using the ideal gas law, doing the mole to mole relationship, and using the ideal gas law here at the end. First off, any questions on how to do that there? Now, where Avogadro's law really sort of comes into play and it's really beneficial is the relationship at constant temperature and pressure is really the moles and the volume are the same, which means if you could recognize this in this type of stoichiometry problem, and once again, it does have to be constant temperature and pressure and everybody's got to be gases, you can basically just do the stoichiometry starting with the liters. So as we talked about earlier, we could say that when we look at the equation for every 3 liters of H2, there would be 2 liters of NH3, and that's equivalent to saying 3 moles of H2 is equal to 2 moles of NH3. So because we recognize this as sort of being under the situation, we actually could avoid pretty much all of this calculation, and we could just start with the 5 liters of H2, do a liter to liter relationship from the equation. 3 liters of H2 gives us 2 liters of NH3, and that would be 5 times 2 divided by 3 is 3.33 liters, give or take with rounding, pretty much the same thing. And you're done here in a very, very quick step here. So let me just actually pop it on the next page here. Go back here. So again, we did 3 liters of H2 equals 2 liters of NH3. So starting with our 5 liters of H2, gives us our 3.33 liters of NH3. So you can see it can definitely save you some time without having to use the ideal gas law in both situations. But again, it definitely has to be at constant temperature and pressure to use this part of it. Now, if it's not constant temperature and pressure, you can still do the 2 ideal gas laws up front and then at the end. But if it is constant temperature and pressure and everybody's gases, you could jump right into that stoichiometry. Yes. So in this particular case, if we back up my question, wherever my question went, where did my question go? I wrote it somewhere here. There it is. So my original question was here, which was basically 5 liters of H2, how many liters of NH3 at 295 Kelvin and 1.35 atmospheres. So since they only gave us basically 1 temperature and 1 pressure, you could assume that that's the temperature and pressure for everybody. It doesn't change. The other way would be they would just frankly not maybe give you a value and just say at constant temperature and pressure. And that would be how you would know it. But again, in this case, they really only gave us 1 temperature and pressure value. So exactly. So that's the only, it's kind of like what we just used with the 1 mole equals 22.414. You can only use that if it's at STP conditions. You can only use this to sort of shortcut stoichiometry if it's at constant pressure and temperature. It doesn't really matter what the temperature or pressure is, but as long as they're being held constant and it's stoichiometry, you can kind of shortcut and do that if you're looking for a volume to volume relationship. Yeah. Other questions? Because the real truth is the reason you can do that is pretty much you basically did opposite gas law problems here. 1.35 was on top, that was on the bottom, that was on top, that was at the bottom. So they basically cancel each other out oppositely when you do it individually. So you can just kind of go right to the liter relationship. Other questions? And obviously the gas constant cancels each other out. So you basically got just the stoichiometry part that's left at that point, basically, yeah. All right. Any questions on gas stoichiometry? No. All right, so go. The next thing we're going to then talk about is partial pressures. So the idea of partial pressures, which is sometimes referred to as Dalton's law of partial pressures, does sound very difficult, but it's sort of a simple sort of concept in the sense of when we talk about pressure and what is basically exerting pressure. If we have a container that only has, say, gas molecule A in it, as that gas molecule A is flying around, basically the total pressure is basically all a result of the pressure that's basically being caused by gas molecule A that's flying around. When we do have a container that has different gas molecules, maybe gas molecule A, maybe gas molecule B or C flying around, the total pressure here is actually a result of the pressure of gas A plus the pressure of gas B plus the pressure of gas C. They're all contributing to the overall pressure of that mixture of gas. The total pressure, by the way, is like your barometer reading, like you did in those experiments. You took the barometer reading, that would be like your total pressure. These are sometimes referred to as partial pressures. So these guys are sometimes referred to as partial pressures because they each partially contribute to the overall pressure of that mixture. So really the total pressure in a mixture of gases is just really the sum of each of the partial pressures together. How do we get the partial pressure? Well, most commonly we use PV equals nRT. So the ideal gas law is essentially what we use to find the partial pressures of each gas in a mixture. So let's talk a little bit about that. Because a gas in a mixture is basically in the same container, the temperature for both gases is usually the same. The volume for both gases is also the same. So because they are basically sitting in the same container in the same room, temperature and volume for every gas is flying around, then there will be the same. So when we look at PV equals nRT, like it shows there, and we solve for P, we have the temperature, we have the volume, we have R. So really the only thing that usually changes is the number of moles of each gas. Now, because this is an ideal situation, in an ideal gas, even though they're both in there together, it's assumed that we could look at them as kind of being in there by themselves. So in that ideal situation, as we talked about earlier, there's really no interaction between the different gas molecules. So we really could do sort of in this example here, two separate problems, one for each gas where we solve for P for each gas individually. The total pressure, we just add them all together. So let's take a look at one here. Actually, let's take a look at that. We'll come back to that in a second. Let's try one here, which is 5 grams of helium. Gas is added to 5 grams of neon in a 2.5 liter container. The temperature is 27 degrees Celsius. Calculate the partial pressures of each gas and the total pressure. And helium is 4.003. And neon is like 2018. All right, we're looking for 3 things. The partial pressure of helium. Okay, let's take a look here, see how we're doing. So in this case, this is a partial pressure problem. We basically have a mixture of helium and neon in the same container. They're both basically causing pressure in that container. Once again, sort of in an ideal situation, we could assume that even though they're in there together, we could really just treat them like they are kind of in there by themselves in that ideal situation. So really, in this case, as we talked about, we can use PV equals nRT really for both gases individually. Once again, though, because they are in the same container, the temperature will be the same for both of them. So we have that. We also have the volume will be the same for both of them because, again, they're in the same container. Once again, we always have R. So really, the one thing that we're missing is the moles for each of those gases to be able to solve for the pressure. So that's going to require us just to do a gram to mole conversion for each of these. So we'll do that to start with. So helium here, 4.003 grams per mole. And 2018 grams per mole of neon. And in this case here, 5 divided by 4.003, 1.249 moles of helium, and 5 divided by 2018 gets us 0.2478 moles of neon. At this point, we now pretty much have everything we need for each of the gases to use the ideal gas law. So doing it for helium first, that would be T divided by V. We will put our mole our R, which is 0.08206. Our temperature, which is 300 when we convert that into Kelvin. So we want to take 27 plus 273. Make sure, again, we do convert it to Kelvin here. Divided by the volume here, which is 2.5 liters. That gives us 1.249 times 0.08206 times a 300 divided by a 250 and a 12.3 atmospheres for our helium. That would be the partial pressure of helium in this mixture. We'd basically do the identical calculation for neon. The only difference is going to be the moles. So our partial pressure of neon would equal nRT divided by V. Here we would use our neon's moles, which is 0.2478, 0.08206. Going to be the same temperature as it's in the same container and the same volume as it's in the same container. And that would get us 0.2478 times 0.08206 times the 300 divided by 2.5. Going to give us about a 2.44 atmospheres. And that would be the partial pressure of neon in this particular mixture. First off, any questions on either of those two? To find the total pressure here, we simply just add those two together. So the total pressure in this case would equal the pressure of helium plus the pressure of neon. So that would give us 12.3 plus 2.44 gives us 14.7 atmospheres as our total pressure in this case. So it really is just the ideal gas law sort of used twice in this case, individually for each gas molecule, temperature, volume going to be the same for everybody because they're all in the same container. Any questions on that there? To figure out the moles, is that what you're asking? Are you talking about sig figs or? Oh, sig fig, yeah. Yeah, well, really, this is 3. I just tried not to round too much there, so I took it to an extra digit and stuff like that. But technically, that would have been 3, and then pretty much that's why we ended up with kind of. You had like 1.25. Yeah. So in this case, sig fig wise, technically speaking, if we kept track of it, this guy would have been 3, which would have ended here, which means when we did all this, basically we would have ended with 3. And then when we added, we would actually just went to 1 decimal place because that one had 1. So you should have ended here. Even if you did yours, you should have ended. Yeah, you should have ended at, because the last thing you did was adding. So you should have had basically 1 decimal place and 2 decimal places, which should have gave you back to the 1 decimal place at the end. Yep. Other questions? The major contributor here is which gas to the pressure? It is helium, right? It's contributing 12.3. The reason for that is helium is much lighter. It's only 4 grams versus 20. Because it's lighter, it's actually moving faster, and it would account for more collisions because of that, because it's really moving faster. And that's why we see a greater pressure for helium versus neon in this situation where we have the same basically temperature and situation that's going on. Any questions on that there? All right, here. Now, another situation that could occur, which is exactly what we did on the second experiment, I think, which was pretty much just set up right here. You had some potassium chlorate and you started to heat it. As you started to heat it, oxygen gas was generated, and the oxygen gas had nowhere to go but to follow the tube. And basically this jar, just like you had water in it to begin with. And at some point the gas came in and also replaced the water that was in there. In addition to the oxygen gas in this case that we collected, we did get some water vapor that came in there as well. As a result of sort of doing this experiment in water, the heat from the experiment will generate some water vapor and you collected a bow. So in this situation, it does create a partial pressure situation where the total pressure is the pressure of the gas you're collecting plus the vapor pressure of water, which is what that is referred to. The vapor pressure of water, as you found, and it's still up there in case you need it, is on the board and on a table. It is typically a table value that you would look up based on temperature. And basically, we do need to do a correction to the atmospheric pressure. So in our experiments, our total pressure, once again, was the barometer reading that you took off of the digital barometer here. But the total pressure does need to be sort of adjusted to account for, really, in this example here, just the oxygen gas. So the total pressure would be the pressure of the oxygen gas plus the pressure of vapor, pressure of water, which means since we're really interested in the oxygen here, we would subtract the total pressure, we'll take off that water vapor pressure. And this will give us really just the pressure of the oxygen gas, which in this example is what we were interested in. It's sometimes referred to as dry gas, the pressure of the dry gas, because you subtracted off water's contribution to it. So sometimes people will refer to that. I think maybe your lab will as well. So that's another very common sort of partial pressure situation. Happens a lot. It actually happened in both experiments that we did. The very first one as well, right? We had the big tube and it was put into a big thing of water, right? And the tube was filled with water. And as the gas came in, it replaced the water. So we collected water vapor in that situation. And on the second one was identical to what we just looked at. Yeah. Yeah, so in the lab where it talks about, the pressure of the dry gas, that is which is the barometer reading, and you subtract off the vapor pressure water, which would be what you got from that. And the purpose of that is that should ideally give you, in the case of, say, our second experiment, that would give you the pressure of just the oxygen gas, which is basically what we're interested in. And then the first experiment, it would give you the pressure of just the hydrogen gas, which is just the gas that you're interested in. So the water in this situation, when we do have the total pressure, is the pressure of the gas plus the pressure of the water vapor. The water vapor is basically just a byproduct of how the experiment was done. So it's just generated as a result of how you're collecting the gas and not really a result of the actual reaction that you're doing. So that's why we usually will subtract it off to get to just the gas that we're interested in those cases. Other questions on that? All right, so why don't we try one here? A sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr. The vapor pressure of water at 30 degrees Celsius is 31.824 torr. What is the partial pressure of oxygen in atmospheres? Okay, so let's take a look. So in this situation, this is really a partial pressure situation where we collected the gas, much like we did in our experiments. How do you know it's this type of problem, if it's just a book problem or something like that? You really have a couple keywords. One is this one right here, which is saturated with water vapor, collected over water, or something that mentions something about collecting the gas over water is an idea where it is this partial pressure situation where, again, our total pressure here would be the pressure of the gas we're interested in plus the vapor pressure of water. In this particular case, they were nice enough to give us the vapor pressure of water. We did have to go look it up. But if we did need to look it up, obviously we would need to look it up in the table based off of the temperature. We also were given the total pressure, which would be like our barometer reading in this case. That means 753 torr would equal the partial pressure of oxygen plus 31.824 torr. That means the pressure of oxygen would be 753 minus 31.824 torr. And that would get us about 721 torr, which if we wanted to convert to atmospheres, we would divide by 760. And that would give us something like 0.949 atmospheres. Any questions on that? So in each of the experiments that we did last week, you basically needed to do this. And that should be the pressure that you should use in your calculations for each of the gases. So that should be really the pressure that you use for the hydrogen gas and the pressure that you use for the oxygen gas, the pressure after you subtract off the vapor pressure of water from the barometer reading or the atmospheric reading. Question on that there. Okay, let's go back and just that thing we skipped there and talk about sort of a third way that you might come across a partial pressure situation, which is this. So occasionally in gas problems, probably not too much in our class, but occasionally in gas problems, you may have a mixture of gases where maybe you don't really have enough information to calculate the pressures using the ideal gas law. But if you have enough information about sort of the gas mixture where you have a way to get to the moles of each gas, and you know one of two things, you either know the total pressure or the partial pressure of a gas, you then could actually be able to solve for the total pressure or partial pressures depending on what you're looking at, even without using the ideal gas law. The basis of that is what this is. This X is what is known as the mole fraction. So that is the mole fraction. And we calculate the mole fraction as kind of like a percentage without multiplying by 100. So it basically is the moles of the gas you're interested in divided by the total moles. So it's basically the moles of the gas you're interested in divided by the total moles in that mixture. Again, here we do not multiply by 100, so it's not a percentage. So it'll come out like a point number or something. And we can use this formula on the bottom, which is the partial pressure of a gas is equal to the mole fraction times the total pressure of that gas. So for example here, if we were told we had a total pressure of 2.55 atmospheres from a mixture of helium, we'll do the of 5 grams of helium and the 5 grams of neon in this case. So we want to know what is the partial pressure of helium and neon in this mixture. So in this particular case, we really are only given grams of each of the gases. So we do have enough to get the moles, but we don't really know the temperature here, although we do maybe know the total pressure. You know, we don't know the volume either. So we don't really have enough information to get into the ideal gas law. So we could use the mole fraction here because we do have enough information to get to moles for each of these guys. And that's enough information to allow us to figure out what we're looking for. So in this particular case, we will use the moles of helium and the moles of neon in the previous problem. So maybe we'll just steal the numbers there. Which way was it? It was this way, I think then. Yeah, so we'll just steal the same number since we calculated earlier. So that would give us 1.25 moles of helium and 0.248 moles of neon. So 1.25 moles of helium and 0.248. Okay, so I just stole the numbers there. So I used the same numbers. Again, obviously use the molar mass to get to those numbers. So what we could do is figure out the mole fraction for helium. And we could get the total moles by just adding those together. So it would be 1.25 plus 0.248 gives us a total moles of 1.50 moles. Our total moles. So the mole fraction of helium would be helium's moles, which is 1.25, divided by the total moles, which is 1.5. And that would get us 1.25 divided by 1.5, about 0.833 moles, or actually no moles, just moles, just a number. We could do the same thing for neon. The moles of neon was 0.248 divided by the total moles. And that would get us 0.248 divided by 1.5, 0.165. So those are the mole fractions for helium in this mixture and really for neon. And obviously when you add those together, you should get the total moles of what we got there, 0.248 divided by 1.5. There we go. All right. Now, when we got this here, we now can use our equation, which is the partial pressure is equal to the mole fraction times the total pressure. So in this case, the partial pressure of helium would equal the mole fraction, which is 0.833 times our total pressure, which was 2.55 atmospheres. So this was our total pressure here. And that would tell us it's about 2.12 atmospheres. It's the partial pressure of helium. We could do the same thing for neon. We would take its mole fraction, 0.165, times it by the total pressure of 2.55, 0.165 times 2.55, 0.421 atmospheres would be the partial pressure here of our neon in this case. Any questions on that? So this is a situation where if you're not given really enough information to ideal gas law, but you're interested in partial pressures or even total pressure, if you have enough information to get to the moles of each of them, each of the gases, and you knew one of those two things, either, like I said, the total pressure like we did here, or the partial pressure of just one of the gases, you'll be able to figure out everything else, kind of doing it that way. I would say probably not too many times you'll come across that here, but it is sort of another way that you could kind of do partial pressures. Any questions on that there? The mole fraction really is a percentage without the percentage there. So basically when we get 0.833, basically means it's made up of 83% of helium in that mixture. And the 0.165 is basically it's like 16% or so of neon, right? So we again see we have a lot more percentage of helium flying around there, also contributing to a lot more of the pressure as well. So kind of the mole fraction is kind of like the percentage of things there without making it a percentage when you do it. Any questions on that there? Okay, so one last thing here, I think, to talk about in this chapter. We did that guy. Did that. All right, so last thing we're going to talk about again is some of the kinetic molecular theory of gases, some of which we've talked about as we've gone through these different sort of gas laws. Gases, as we've talked about, are tiny particles, either atoms or molecules. These particles are so small compared to the distances between them. The volume of the individual sort of gas molecule is assumed to be negligible or zero. So as we mentioned earlier, that's really one of the things here that makes something an ideal gas, that under sort of normal situations, the volume of the gas is really small compared to the container it's flying in. So as we talked about, that is why we usually will sort of focus in on the volume of the actual container that's there rather than the gas itself. And again, the idea is it's flying around the entire container. So even though the volume is really small for the gas, it is taking up the whole volume of the container in an ideal situation. The particles are in constant random motion colliding with the walls of the container. Again, it's the number of collisions that really cause the pressure that we assert with gases. So obviously, as the number of collisions increase, we would expect an increase in the pressure, and vice versa. As the number of collisions go down, we would expect the pressure to go down. Number 4 here is really the second thing that makes something an ideal gas, which is the particles are assumed not to attract or repel one another. So under ideal conditions, the idea here is they really will not interact with one another, even if they're in the same container. And that's why, as we just did in these last partial pressure type problems, we're able to essentially just assume that each gas was in there by itself. We could do separate calculations for each of the gases. What would happen if they did interact with each other? Well, if the idea that the gas is heading towards the wall and making a collision that's causing the pressure, if there happens to be another gas molecule where he may be attracted to, it might slow him down a little bit, and he wouldn't hit the wall as fast or as many times, and it could affect the overall pressure of that mixture if there was interactions between them. Also, if they were repelled by one another, they would go away from one another and also could affect things. We do again see that occur in what is referred to as real gases under really high pressures and low temperatures. You'll talk more about it when you go into 1A. 5, the average kinetic energy of gas molecules directly proportional to its Kelvin temperature. So that's relating to what we talked about earlier. Obviously, if you increase the temperature, you increase the energy, the gas molecules start to fly around a lot faster. And obviously the opposite is true. If you lower the temperature, everybody loses a little bit more energy. They're not flying around as fast, and obviously that can have some effects. So these are just some of the relationships that we talked about through those gas laws. Again, the higher the temperature, as we just talked about, they will be moving faster and hitting the walls. Pressure and temperature, if we do not have that volume to adjust, if we do that and we do increase the temperature, that would obviously result in more collisions and more pressure. And if we lower the temperature, less collisions and less pressure. If we have sort of the volume to adjust like it does in the Charles law situation, the volume will adjust as the temperature adjusts. Again, that's able to give everybody more room if needed to keep the number of collisions relatively constant and the pressure constant, and vice versa. If we lower the temperature, then the volume will decrease to kind of squish everybody together and allow the number of collisions to remain basically the same, which is sort of what we see in this situation here. Any questions on gases, gas laws, any of those things? All right, so that wraps up chapter 13, which once again is not on the exam on